All right, hey everyone, I'm Avnish. I'm an 18-year-old quantum computing enthusiast, and I've been working on using quantum annealers to solve the vehicle routing problem with Shantom and Ashish. So that's what we're going to be talking about today. So real quick, I'll go over the outline. So we're going to talk about what the vehicle routing problem is and how it works. Then we'll talk about quantum annealing and how we can use that to solve optimization problems. And then I'll explain the exact QWorld formulations that we used. Then Shantom will talk about cluster root heuristics and root cluster heuristics. So these are approximate formulations of the vehicle routing problem. And finally, Ashish will talk about the GPS solver, our numerical experiments, and further exploration that can be done into the vehicle routing problem with quantum annealing. So let's get into it. So the vehicle routing problem, you can think of it as the quintessential problem that a delivery company would care about. So they have a depot with a few trucks, and they have maybe 10 clients that they need to visit, or 10 deliveries that they have to make. They want to create a route for each of their vehicles such that all these clients receive their deliveries. And their goal is to minimize either the length of the path vehicles take, or the amount of time trucks spend on the road, or essentially the price of the gas that they have to spend. And that's basically what the vehicle routing problem is all about, minimizing this cost. So we have a set of n+1 nodes where node 0 represents the depot, and the nodes 1 through n represent the clients that need to be visited. And we have a set of m vehicles. We also have a cost matrix for which each element, the cost Cij, represents the cost of moving from node I to node j. Again, we have an objective function, and a total is to minimize the cost of the routes that the vehicles take. So any quantum computer solves a QWorld by encoding it as a cost Hamiltonian. And the ground state of this cost Hamiltonian is the solution to our problem. So you can think of this cost Hamiltonian as a matrix whose lowest eigenvalue represents the cost, and the vector corresponding to that eigenvalue represents the optimal solution or optimal configuration. The adiabatic theorem states that if we start with a physical system in the ground state of a certain Hamiltonian, and we slowly evolve it into a new Hamiltonian, then we will remain in the ground state. And this is important because the ground state of our cost Hamiltonian is, again, the solution to our problem. So we start in the ground state of a well-known Hamiltonian H0, and the ground state of H0 is usually the superposition of all qubits, which is very easy to prepare. And then we slowly evolve it into our cost Hamiltonian by turning on biases and couplers in our quantum annealer. So we start at time 0, so lowercase t is equal to 0. And as lowercase t slowly increases to capital T, which is the total runtime of our computation, then this term vanishes and we end up with HC. And the adiabatic theorem states that if we do this slowly enough, we'll end up in the ground state of HC. So quantum annealers, by the way, they don't actually do it this slowly because this can take a long time. They are less idealized version of adiabatic quantum computing, where they run the anneal, which is what it's called, much quicker, and they do this multiple times so that you can take the best solution. So exact VRP formulations, basically we're representing our problem with a QWorld that's an objective function whose minimum is the one we want to find. And we also add these constraints on our variables to ensure we maintain the reality of the problem. If our optimization problem is formulated in such a way that the solution to our QWorld is the optimal solution, then that's called an exact formulation. And if we formulate our objective function in a way that its minimum is not necessarily the best solution, it's just a really good solution, then we call it an approximate formulation. So theoretically, if we take an exact formulation of our problem and run a quantum computation on it, we should get the best solution. But that's almost never the case, or it's very rarely the case, because there may be errors due to noise from the external environment. So I'm going to start explaining the two exact solvers for the vehicle routing problem. The first one is the full QWorld solver. The way this formulation works is that we have these binary variables xitk, and xitk is 1 if the ith node is visited at the tth time step by the kth vehicle, and it's 0 otherwise. So that's a bit of a lot, so feel free to pause to digest that. The first term of our objective function represents what happens at time step 1, which is when all the vehicles leave the depot. So that's why we have C0i, which is the cost from the depot to node I, and we sum over all nodes I and all nodes and all vehicles k. And we also have the binary variable corresponding to what happens at the first time step. Then we have what happens at the final time step. So the final time step is n plus n, and then we have the cost from all of these nodes. We're summing over the cost from all of these nodes to the depot, because all vehicles must return at the last time step. And of course, we're also summing over all vehicles. Now, the next term in our objective function is really the meat of the whole problem, because notice we have a variable xitk and then xj t plus 1k. So basically, if xitk is 1 and xj t plus 1k is 1, that's basically like saying that you start like at a time step t, the vehicle's at a certain node, and then at the next time step, it's at a different node. So it's definitely traveled a path from one node to the other. So we want to take into account the cost from, for example, node 4 to node 3, as I've drawn it here. And again, we're summing over all possible time steps, all of the nodes, and all of the vehicles. Now we have to apply quite a few constraints on the variables to ensure that we get a valid solution that would sort of make sense in the real world. I'm not going to explain these constraints too much in depth for the sake of time, but feel free to pause and look at these to make sure that these formulations as they've been written actually make sense. So the first constraint ensures that at any given time instant, exactly one vehicle visits exactly one client or the depot. The second constraint ensures that each client is visited by one vehicle throughout all the time steps. So for a given node I, basically it must be visited by at least one vehicle. So if we sum over all vehicles k, at least one of these x variables must be 1. And in fact, exactly one of them must be 1, because we don't want to visit the same node multiple times. Here are a few more constraints. So first of all, we have this constraint that says that every vehicle visits the depot at some time step. And notice we're starting from t equals 1. This is because we're not including the first time step. Obviously at t0, every vehicle is at the depot, but at some point, every vehicle must return to the depot. We've got a little bit of a glitch there. The fourth constraint ensures that each vehicle visits at least one client. If we've got 3 vehicles, we don't want to waste them by only having one vehicle do the job for us. So that's what this constraint is for. And as you can see, it's an inequality constraint, which normally we would have to convert this from an inequality to an equality constraint. And that requires adding extra slack variables, which I'm not going to talk about because these days D-Wave's platform allows you to do that under the hood and abstract away that process. Constraint number 5, if a vehicle has visited a client at time step t, then it must visit another client or the depot in the next time step. So you can't just wait at a single node for multiple time steps. You must move on. And then constraint number 6, if a vehicle has visited the depot at time step t0, then the journey for that vehicle is over. So once the vehicle returns to the depot, we don't want it to go visiting other nodes. Once you're back at the depot, you're done. And now here's an extra add-on that we may or may not add depending on what we want to do. So this is the full QWorld solver with time windows. The idea behind time windows is that maybe for each client, there's a certain window where we want our truck to arrive. Maybe because that truck has to do some kind of service for that client. So each time window has an earliest time and a latest time. So if a vehicle arrives before the earliest allowed arrival time, then it must wait at that node until maybe the customer is available. And if the vehicle arrives too late, well, that's considered an invalid solution, and we just throw that away. We use this ATK to symbolically represent the arrival time to the node visited by vehicle K at time step T. And we have these omega TK variables, and these are integer variables that the quantum annealer optimizes. And these integer variables denote the waiting time at the Tth visited city by vehicle vehicle K. That should be K. And here's how we express A with the following recurrence relation. So obviously, at the first time step, a vehicle has gone from the depot to some node I. So that's why we have the cost from 0 to I, and we're summing over all of them. And in theory, only one of these possible X values will be 1 for a given vehicle K. And then we have a recurrence relation. For any ATK, we take the arrival time at the previous node plus the amount of time the vehicle spent waiting at that node, maybe if it arrived too early. And then the next term is the cost for getting from the previous node to the current node. And of course, we can convert this into an explicit form because this is much easier to encode on a D-Wave annealer rather than the recurrence relation. So like I said, we have an earliest possible arrival time for each node. So that's represented by the letter E. And the latest allowed arrival time is represented by the letter L. And we want to bound our variables ATK plus WTK. We want to bound this between the earliest and latest arrival time for a given node. All right, finally, I'll talk about the root activation solver, which is another exact solver, but that formulates the problem in terms of edges rather than just nodes. So we have these binary variables xij, which are 1 if the edge ij is traversed by a vehicle. So in other words, if the edge from node I to node j is activated, then xij is 1. We also have these other sets of binary variables yik, and yik is 1 if and only if the ith node is visited by the kth vehicle. And finally, we also have these integer variables ti, which represent the time taken for any vehicle to visit the ith node. So our objective function looks a lot simpler. It's just a sum over the cost of the activated edges, and we want to minimize this objective function. So we do have a few constraints though. So one constraint is that each client node must have exactly one edge directed away from it and one entering it. So that is represented by these two constraints. We also want to ensure that each client is visited by exactly one vehicle. So we have these yi variables. So for a given node I, the sum over each vehicle for those y variables should be 1. So that ensures that only one vehicle visits node I. Exactly m vehicles must come from the depot and exactly m return to the depot. So m is the total number of vehicles. And we want to ensure that there are m vehicles leaving and m vehicles entering. So this here ensures that there are m edges leaving the depot, and this ensures that there are m edges returning to the depot. We also want to ensure that if there is an edge from node I to node j, then both the ith and the jth node must be visited by the same vehicle. So this seems pretty obvious. If we have a node here and a node here and an edge between them, then obviously there is one vehicle that is traveling that path. But this constraint ensures that that is the case. Finally, we need to make sure that each vehicle is used exactly once. If we've got 5 trucks in our depot, might as well use all 5. We don't want to keep 4 of them sitting in the depot while one vehicle does the job for everyone. That's not as efficient. And the last thing is a bit of a tricky one. So this is the subtour elimination constraint. This specific way of doing it is called the MTZ constraint. And let me show you. So if you don't include this constraint, then you might get solutions like this. So notice this is our depot right over here. Our problem is instances for 5 clients and 2 cars. And notice that we do have 2 cars leaving the depot, and we do have 2 of them returning to the depot. But what's weird here is that these 2 nodes over here are disconnected from the depot. It's almost like a third vehicle has been created out of thin air that just satisfies these 2 clients, but never ends up returning to the depot because the constraints ensure that only 2 cars return to the depot, since there are only 2 cars. So the MTZ constraint is necessary to solve all of this. And notice here it says B is a large number. So basically, if you make B a very large number, then that ensures that if this constraint is violated, then the cost will be very high. And if the cost is very high, then you just won't use that solution because it's not an optimal solution. So that's it from me. Now I'm going to pass it over to Shantom, who will talk about more approximate formulations of the problem.
Hi everyone, my name is Shantom. I'm a recent graduate in physics and electrical engineering from Vesselin, India, and I shall be presenting to you the next few slides in this presentation. More specifically, I shall be talking about the root cluster and cluster root type of heuristics for solving the vehicle routing problem. So to start off, let us look at the cluster root type of heuristics. So the cluster root type of heuristics are essentially based on 2 phases for solving the vehicle routing problem. In the first phase, we cluster the set of nodes that we have, the set of client nodes that we have into k clusters. The k is the number of vehicles, and we assign each vehicle to one cluster. In the second phase, we solve the traveling salesman problem for each of the clusters assigned to each of the vehicles. So examples of this kind of solver include the DB scan solver and the maxcut partitioning solver. So in the DB scan solver, we have a classical algorithm, the PV-scan algorithm for the first phase, and we use a quantum computer to solve the traveling salesman problem in the second phase. In the max-cut partitioning solver, we have a fully quantum solver where we use quantum computers to do clustering as well as roughing. So let us take a deeper look into the max-cut partitioning solver. So here is the first phase of the max-cut partitioning solver, essentially the clustering phase. So to cluster using a quantum computer, we will again need to formulate the clustering problem as a QWorld problem, and this is done on this slide. So we have a set of binary variables xij, which indicate which node is assigned to which cluster. So xij is designated to be 1 if and only if the ith node is assigned to the jth cluster. Of course, every node has to be assigned to exactly one cluster. So we have this constraint in which when we sum over j, that is set of all clusters for each node, we must get 1. It essentially says that every node must be assigned to exactly one cluster. So now let's take a look at the objective function. The objective function is a minimization over this sum here. And if you look at this sum, we have a sum over I, j, and k, so three indices, Cij, Xik, Xjk. So let's unwrap this a bit. So what does Xik, Xjk tell us? Xik is 1 if the ith node is assigned to the kth cluster, and Xjk is 1 if the jth node is assigned to the kth cluster. So this entire term, every single term of this summation is 1 if and only if the ith and the jth node are assigned to the same cluster k. And if that is the case, if they are actually assigned to the same cluster, we add Cij to the total sum, and we then minimize over this sum. So this sum is essentially the sum over the weights of edges between nodes in the same cluster. And minimizing over this sum is essentially equivalent to maximizing over the sum of the weights of edges between nodes in different clusters. So when we are minimizing this, we are essentially doing that. That is, we are ensuring that the clusters are essentially separated as far apart from each other as possible in terms of the cost function Cij. And so that is how you would derive or at least motivate how this objective function comes about. As a side note, note that if we have only two clusters, then this formulation essentially reduces to the well-known max cut problem, and hence we call this the max k cut formulation. That's generalization of the max cut problem to k clusters instead of just two clusters. And we use this formulation to cluster the client nodes in the VRP into k clusters. Once that clustering has been done, we need to solve the traveling salesman problem for each of the clusters. So the formulation of the traveling salesman problem is shown here on this slide, and you will notice that this is very similar, almost identical to the full QWorld solver that Avnish has described previously, except now instead of Xijk, we simply have Xij because we are considering each vehicle one at a time. So Xij is 1 if the salesman, or in our case the vehicle, is at the ith node at the jth time step, and it is 0 otherwise. The objective function is essentially the sum of the weights of edges that are included in the route of the salesman or vehicle, if you will. So the first term over here is the first section of the route from the depot to the first node that is visited by the vehicle. Second term is the last section of the route from the route, the edge from the last node in the vehicle's journey to the back to the depot. And the last term over here is every edge in between that the vehicle passes through. So xin, xjn plus 1, these terms, xin is 1 if the vehicle is in the ith node in the nth time step, and then xjn plus 1 forces the vehicle to be the jth node in the f plus 1th time step. If that is the case, we should include Cij in the sum because that section of the route is being visited by the vehicle. Constraints are also quite simple. The sum over j, and the sum over j xij equal to 1 for all I. This says that for every node I, when we sum over all the time steps, we must get 1, which means that every node must be served exactly once at exactly one time step by a vehicle. And the second constraint over here, we're summing over I instead of j. This essentially means that the vehicle can only be in one node at any given time step. So once we solve this problem for each of the vehicles, we will have a final solution for the vehicle routing problem. Note that we will need to access the quantum computer k plus 1 times if we solve this naively. That is, we need to access the quantum computer once for the clustering phase and k times for solving k TSP problems for each vehicle. But that can be simplified. So here is the parallelization of the TSP solution. So the graphs that you see in this figure are shown with respect to a problem that has 5 nodes and 5 client nodes and 2 vehicles. So we are considering the QWorld graphs for the second phase of the problem, that is the traveling salesman problem phase. So as you can see, both of the TSP graphs for each of the vehicles are neatly separated out into two groups, which makes sense because we have already completed the assignment of clusters to vehicles, and now the TSP solution for each of the vehicles will be done parallelly. So the cubographs of these problems also separate out neatly into k clusters, in this case 2 clusters, and they can be embedded parallelly into the D-Wave hardware. And all of the k TSP solutions for the k vehicles may be found in parallel. So that essentially means that we need to access the quantum computer only twice instead of k plus 1 times to solve the VRP via the Maxwell partitioning solver. So here is a sample solution. We have a cluster on the right and a cluster on the left. The cluster on the left here is a set of 3 nodes that is assigned to one vehicle, node 5, 3, and 2. And the cluster on the right, indicated in green, nodes 1 and 4 are assigned to the second vehicle. Moving on to the root cluster type of heuristics. So in this type of heuristics, we essentially perform similar steps as in the cluster root type of heuristics, but the ordering of the phases are reversed. So we first solve the traveling salesman problem for the entire set of nodes. We assume a single vehicle is present in our vehicle routing problem and solve it by treating it as a traveling salesman problem. And in the second phase, we partition the TSP route that we have obtained into k parts, and we assign a small section of the TSP route to the k different vehicles. So examples of this type of solver are the solution partitioning solver and the shortest path partitioning solver. We shall take a look at the solution partitioning solver next. So here is the first phase of the solution partitioning solver, the traveling salesman phase. So in this phase, we are essentially considering the same problem that we had considered for the Maxwell partitioning solver. The problem with 5 clients and 2 vehicles, except now we have only one vehicle because we're treating it as the traveling salesman problem. And this is the route that is found by solving the TSP for this problem. The formulation for the TSP is something that I have already described previously, so I will not elaborate on that again. Once we have found this route, we will need to break it down into sections, into 2 sections for 2 vehicles. So let us do that. So here is the second phase. So this graph over here is essentially a reordering of the graph in the previous slide according to the TSP solution. The TSP solution that has been found is 5, 3, 2, 1, 4, and back to 0. What we want to do is assign one part of this route to one vehicle and another part of this route to the second vehicle. So that will require us to cut this route at one point exactly. We may cut the route at the edge between 5 and 3, between 3 and 2, between 2 and 1, or between 1 and 4. So suppose we cut the route at the edge between 2 and 1. That would amount to assigning nodes 5, 3, and 2 to the first vehicle and assigning nodes 1 and 4 to the second vehicle. So in this case, the first vehicle will take the route 0, 5, 3, 2, and back to 0. So first vehicle would have to travel an additional distance corresponding to the cost between 2 and 0. And similarly, the second vehicle, which will travel route 0, 1, 4 and back to 0, will have to cover the additional distance C01. Except no vehicle will really cover the distance between 2 and 1 distance. So the additional cost incurred if we cut the route at the edge between 2 and 1 is C20 plus C01 minus C21. And similarly, we can figure out the cut costs that is incurred by cutting the route at each of these points. Finally, to partition the route, we simply cut the route at the edge that incurs the minimum cut cost. So we do that here, and it turns out that it is optimal, in fact, to cut the route for this particular solution at the edge between 2 and 1. So we assign the nodes 5, 3 and 2 to the first vehicle, and the nodes 1 and 4 to the second vehicle. As a side note, the solution partitioning solver is especially good at being generalized to the capacitated vehicle routing problem. We shall not outline that in these slides, but I shall refer anyone interested to one of the papers that we have referenced at the end of the slides, the reference one. So now I would like to hand over to Ashish, who will elaborate more on the GPS solver and also on some of the numerical experiments that we have conducted as part of our research.
Hello, I'm Asish and I'm currently an undergraduate at the Indian Institute of Technology, Kanpur, majoring in electrical engineering. Previously, Avnesh talked about two exact VRP formulations, the full QWorld solver and the root activation solver. We will now take a look at another exact formulation of VRP, the GPS solver. This formulation was prepared by Guillermo, Perfect and Sol, and this implementation of the solver is based on their paper on the same topic. The main goal behind this formulation was to find an efficient QWO formulation that minimizes the number of variables. We'll briefly see why we need to minimize the number of variables in one of the later slides. The authors of the paper have given a suitable formulation for the traveling salesman problem, and then they have tried to extend it to a VRP formulation. Okay, now let's take a closer look at the GPS formulation. In the GPS solver approach, instead of keeping information about the exact time step at which a vehicle visits a city, like in the earlier exact solver, the, the binary variables encode information about the order in which a single vehicle traverses the node and the order in which different vehicles start and finish their journey. There are two sets of binary variables in this formulation, xijrk and aij. So the r equal to 0 is in xijrk represents the state of whether the kth vehicle visits node I before node j such that there is no direct edge from I to j. Similarly, r equal to 2 represents the state of whether the kth vehicle visits node j before node I, again such that there is no direct edge from j to I. So xij1k represents the case where there is a direct edge from node I to node j, and aij is set to 1 if and only if there is if and only if I is reached before node j, considering all the vehicles. In this formulation, we shall assume that the vehicles traverse in the order of their indices, that is, vehicle 1 completes its journey before vehicle 2, and so on. Let's take a look at this example, which will make it more clearer. We can see here that vehicle 1 visits node 6 before node 4, and there is no direct edge between them. So x6401 will be set to 1, and x4621 will also be 1. We can see that vehicle 2 visits node 5 followed by node 7. So we can say x5712 will be 1. Now, between node 6 and node 2, how do we know which node is visited first? As I said a few moments ago, we'll follow the convention as in the paper. We'll assume that the vehicles with lower indices complete their journey first. So in this example, vehicle 1 completes its journey before vehicle 2. So for this reason, we will say that X6201 will be 1 and A62 will be 1. The objective of this foundation is to minimize the overall cost of the complete journey of all the vehicles. The objective is simply the sum over all the costs between nodes I and j whenever there is a direct path from node I to j. And all these paths add up to make the whole journey. So there are a set of constraints that these variables need to satisfy. First, for the kth vehicle and the pair of nodes I and j, these pairs can either be connected or not be connected, and there must be a fixed order in which they are visited. This gives the first constraint where among xij01, xij0k, xij1k, and xij2k, one of them must be 1 and the rest of them must be 0. Now we have the second set of constraints. So every vehicle must begin at the depot and end up at the depot. Nearly every vehicle must arrive at a city exactly once and leave each city exactly once. So yeah. Third, the third constraint states that the order in which cities I and J are visited must be fixed. Please note here that it is not necessary that both cities I and J are visited by the same vehicle. This third constraint gives the relation between the type of variables x and a. So xij0k and xij1k together they mean that I has definitely been visited before j. When this is true, considering all the vehicles from 1 to m, only then aij will be set to 1. Otherwise, it will be set to 0 and aji will be set to 1 instead. For the fourth constraint, we essentially have to ensure that the previous constraint is satisfied for each vehicle. Here, it must always be the case that exactly one of xij0k, xij1k, xji0k, and xji1k, one of them must be set to 1 and the rest must be set to 0. Okay. So for the fifth constraint, we have that if a vehicle arrives at a city, then it must leave that city. So if a vehicle goes from kth city to the kth city, then there must be exactly one other city, or there may be the depot that the vehicle visits after the kth city. So the sixth constraint is simply a condition that eliminates the possibility of a cycle. That is, if city J is visited after city I and city K is visited after city J, then it must not happen that city I is visited after city K. That would create a cycle. Note that here I, J, K are distinct and neither of I, J or K is the 0. If, however, one of I, J, K is 0, then such cycles are allowed. So this slide is just evidence of the results we have obtained by running the experiment on delayed quantum annealers like leaf hybrid sampler. So using all the previously described solvers, we have been able to achieve good accuracy till 11 clients and 10 vehicles for at least one solver. Solvers like FQS give a little worse results compared to other exact solvers as we increase the number of clients or cities. On the other hand, The root activation solver gives the exact solution for up to 6 clients and close to exact solution for 11 clients. We'll take a look at one reason for why we get solutions with such different accuracy in the next slide. In order to get to the solution, the formulated QWorld problem has to be mapped to the quantum annealing hardware, and the number of qubits in this hardware grows linearly with the number of variables in our formulation. The current noisy intermediate scale quantum era or NISQ era, we need to be careful about the number of qubits and hence the number of binary variables that we use in our formulation. Because the more the qubits we use, more will be the noise introduced in the overall annealing process, which will further lead to a lower quality solution. In the current slide, you can see that among the exact solvers, root activation solver is the one that uses least binary variables, which explains its higher accuracy compared to other exact solvers. Similarly, among the approximate solvers that Shantom had described earlier, solution partition solver gives more accurate solutions because the clustering phase here is actually done classically, so it is safe from noise. This fact is not true in case of the max cut partition solver MPS. We have already given an implementation for the full QWorld solver for VRT with time windows and a solution partitioning solver for the capacitated vehicle routing solver. In future, we would like to extend our approaches for other variants of the vehicle routing problem, like the multi-depot vehicle routing and the capacitated vehicle routing with time windows, etc. In order to ensure that the connectivity required by the QWorld is maintained, we sometimes need to take multiple physical qubits for a single logical qubit. But again, we would also like to embed our QWorld into hardware in such a way that the number of physical qubits is minimized. So this is a research-worthy topic if we want more control over the number of qubits we want to use. We are also hoping to explore machine learning based approaches to solve vehicle routing problems. One of our team members in our Q research project at QWorld, Justina, who is also a speaker in this conference, has worked on something related to this, that is solving the traveling salesman problem using neural networks. Make sure to check out her talk. This project was originated by Shantom Borah as a project under the Quantum Open Source Foundation Mentorship program under Dr. Vesselin. It is now a part of the Q research project led by Dr. Paweł Gora at QWorld. We would like to thank Dr. Vesselin and Dr. Gora for their constant support. Thank you for listening to this talk. Feel free to reach out to any of us to ask a question or drop a comment. You can find our relevant profiles attached to this slide.